Hello. Glad to see you all again in a video about the universe. Humans have been trying to understand the universe for thousands of years. In the process, we've uncovered countless mysteries. We now know that the Earth revolves around the Sun. The Sun is one of hundreds of billions of stars in the Milky Way, which is itself one of trillions of galaxies scattered throughout the universe. We know how the universe was born, how stars are formed, and how they evolve. However, there are still many mysteries that humans have yet to explain. We don't know how life was formed on Earth. We don't understand what happens inside a black hole. We are still uncertain about the nature of dark energy, and we don't know what the true shape of the universe looks like. In this video, we will attempt to decode one of these mysteries together. Welcome to Wonder Scope, the true shape of the universe. First, let's clarify that the concept of the true shape of the universe is a bit ambiguous. It encompasses both the shape of the observable universe, also known as the visible universe, and the shape of the entire universe, which includes everything inside and outside of the observable universe. The shape of the visible universe is fairly straightforward. It forms a spherical region of space with a radius of 46.5 billion light-years, centered around Earth. This visible universe contains everything we can observe from Earth, either through telescopes or space probes. It's important to note that the word observe in the context of the observable universe doesn't mean that humans can actually observe objects that are 46.5 billion light-years away. Instead, it refers to a theoretical limit. Any object outside of this range will never be detected by us because the light emitted by those objects will never reach Earth. This distance marks the boundary of the observable universe. According to calculations, the visible universe, with Earth at its center, is composed of 68.3% dark energy, 26.8% dark matter, and only 4.9% ordinary matter. This ordinary matter exists in hundreds of billions to 2 trillion galaxies of varying sizes, including our own Milky Way, where we live. Broadly speaking, the visible universe can be imagined as a spherical region with a radius of 46.5 billion light-years, and it may be similar to the visible universe from any point in the universe. It would be convenient if the observable universe were the same as the entire universe. This way, scientists could determine the structure and shape of the entire universe just by observing it. But, as we'll see, the universe is not as simple as it might seem, and the visible universe cannot be the entire universe. As mentioned before, from any point in the universe, we can define a visible universe. My visible universe, for example, may differ from yours by hundreds or even thousands of kilometers, depending on our positions on Earth. The visible universe of Pluto, which is over 5 billion kilometers away, has the same radius, but its scope of observation is different from Earth's. Similarly, someone living in the Andromeda galaxy would see a visible universe that differs from ours by more than 2.5 million light-years. And if we continue thinking about points even further out, like at the edge of Earth's visible universe, we realize that this visible universe would be drastically different from ours. In this way, the concept of the observable universe becomes somewhat vague. It only makes sense for small objects like us on Earth. Moreover, all the best scientific theories about the history of the universe suggest that the universe continues beyond the observable limit, and that it cannot be confined to the boundaries of the visible universe. Let's use an example to illustrate this. If the visible universe were the entirety of the universe, then Earth would be the gravitational center of the whole universe. The movement of galaxies near Earth would be affected in such a way that we would observe certain behaviors in their motion. But, as we know, this does not happen in reality. If the universe were finite and had a diameter of only 93 billion light-years, there would be a boundary or edge where everything ends. However, this idea contradicts the cosmological principle, which states that, regardless of where you are in the universe should look the same in all directions on a large scale. This leads to the conclusion that what lies outside the visible universe must be similar to what lies inside it. In other words, the universe cannot simply end at the edge of the visible universe. Instead, the universe must extend beyond the observable universe. For the universe to remain both homogeneous and isotropic, that is uniform and the same in every direction, it must have a closed-loop structure. If the universe were a closed loop, light from the Milky Way would be able to travel around the universe and possibly come back to Earth several times. This would allow scientists to find multiple images of the Milky Way from different points in its past. However, this also does not occur. Let's temporarily accept the idea that the universe is indeed larger than the observable universe. The next question is, what shape does it have? To be honest, we don't know for sure. Just like a fish cannot know the true shape of the ocean, humans cannot truly know the shape of the universe while we are living inside it. But let's try to analyze it further. According to the theory of relativity, space itself can be curved. This means that the universe can take one of three shapes. It could be flat like a piece of paper, closed like a sphere, or curved like a saddle. Now, you might ask, why are we limiting the shape of the universe to just these three possibilities? Why can't it be shaped like a rice bowl, a can of Coca-Cola, a horse, or even a donut? The answer to that is simpler than you might think. The reason the universe can only have one of these three shapes, flat, spherical, or saddle-shaped, relates to two key factors: the density of the universe and its rate of expansion. While the expansion rate of the universe is something we can observe and measure accurately, the universe's density is something we still don't fully understand. Imagine the universe weighed 1 kilogram. Of that 1 kilogram, 683 grams would be dark energy, 268 grams would be dark matter, and only 49 grams would be ordinary matter, the matter we can observe and interact with. Dark energy is a form of repulsive gravity, and scientists introduced it to explain the accelerating expansion of the universe. Dark matter is a hypothetical form of matter used to fill in the gaps and ensure the accuracy of our gravitational theories. Now, the term dark and dark energy and dark matter does not refer to anything sinister or malevolent. Instead, it simply reflects the fact that these forms of energy and matter don't interact with ordinary matter or radiation in any way, except through gravity. This makes them invisible and difficult to detect using traditional methods. Returning to the main content, the three proposed shapes of the universe represent the three possible states in which the universe can exist: a flat universe, an open universe, and a closed universe. The flat shape corresponds to a flat universe, the saddle shape corresponds to an open universe, and the spherical shape corresponds to a closed universe. Since the expansion rate of the universe is relatively constant, about 70 kilometers per second per megaparsec, the shape of the universe is primarily determined by the density parameter. The density of the universe here refers to the total energy density, which includes the average distribution of ordinary matter, dark matter, and dark energy in space. The density parameter, denoted by omega, is calculated as the ratio of the actual measured density of the universe to the critical density. Critical density is the value at which the universe would reach a state of equilibrium, where the gravitational pull balances with the momentum of expansion. The time frame for this equilibrium is infinite, meaning it will take an infinite amount of time for this to occur. If the actual density of the universe is equal to the critical density, meaning omega equals 1, the universe is in equilibrium, expanding in all directions without any positive or negative curvature. In this case, the universe has a permanently flat state. Essentially, the shape of the universe is governed by the tug-of-war between the momentum of expansion and the gravitational pull trying to slow it down. If the actual density exceeds the critical density, i.e., omega is greater than 1, the density of the universe becomes large enough that gravity overcomes the force of expansion. As a result, space curves into a sphere. Scientists call this a closed universe model with positive curvature. An interesting and somewhat astonishing feature of a closed, spherical universe is that although it is finite, it has no tangible boundaries. A cosmic probe sent from Earth could travel around that universe forever without ever encountering a boundary or edge. There's no fence, wall, or precipice to fall off of. On the other hand, if the density of the universe is less than the critical density, meaning omega is less than 1, gravity is too weak to halt the expansion, and the universe will continue to expand eternally. In this case, the universe's space curves in the opposite direction, forming an open universe with negative curvature, resembling the shape of a saddle. This leads us to the conclusion that the universe can only have one of three shapes: flat, spherical, or saddle-shaped. It cannot take the shape of a rice bowl, a Coca-Cola can, a horse, or a donut. The structure of the universe is constrained by these three possibilities due to the interactions between its expansion rate and density. The final task is to accurately determine the actual density of the universe. Fortunately, scientists have made significant progress in this area. Between 2001 and 2010, NASA's Wilkinson Microwave Anisotropy Probe, WMAP, meticulously measured tiny temperature fluctuations in the cosmic microwave background radiation. This allowed scientists to photograph the universe at a time when it was just 380,000 years old, offering crucial insight into the universe's energy density. From these measurements, the average energy density of the universe was calculated, which was equivalent to a mass density of about 5.9 protons per cubic meter of space. To visualize this, it's similar to distributing a single drop of water evenly across a volume the size of Earth. What's even more remarkable is that this density is very close to the theoretical critical density, suggesting that the universe is flat and infinite in size, with an error margin of only 0.4% as of 2013. In fact, a 2021 study further refined this result, concluding that the universe has a flat shape with an error margin as small as 0.2%. However, it's important to note that these findings do not definitively prove that the universe is flat. They simply indicate that, based on the best measurements and calculations available, the universe is very likely to be flat. Still, scientific consensus is far from absolute on this matter. In late 2019, Professor Alessandro Melchiori from Sapienza University of Rome, Italy, and his colleagues published a study in which they used data from the Planck Space Telescope to examine the cosmic microwave background. Their research suggested that the universe might actually have a closed, spherical shape as opposed to being flat. The researchers pointed to the possibility that gravitational lensing, where the gravity of galaxies deflects light from distant sources, could be skewing the measurements of the cosmic microwave background, leading to the discrepancy in the data. It's important to clarify that this study does not disprove NASA's previous findings, nor does it claim that the universe must have a closed shape. Instead, the researchers believe that the inconsistencies in the measurements might indicate that scientists are overlooking something crucial. In conclusion, the universe is likely to have a flat shape, based on current observations. However, it could also be spherical, and the search for a definitive answer continues. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell to stay updated with Wonderscope. Thanks for watching, and we'll see you in the next video.